Welcome to English 1 at the University of Crete. I'm Noni Rizopoulou, and in this video we'll look into software engineering, which is the discipline of designing, building and maintaining software systematically. It applies engineering principles to ensure quality, reliability and efficiency. Modern software systems are complex, making structured approaches essential. Software differs from traditional engineering because it is intangible. Nothing physical is manufactured, so it can be changed repeatedly at low cost. Requirements also evolve more rapidly, meaning software projects often need iterative and adaptable processes rather than fixed blueprints. While traditional engineering is constrained by materials and physical laws, software engineering deals with logic, abstraction, and user needs. The software lifecycle describes the structured phases a project goes through, from conception to retirement. It provides a framework for planning, organizing, and monitoring development activities. By breaking work into clear stages, the life cycle helps manage complexity and ensures that quality, timelines, and goals are maintained throughout the product's lifetime. The analysis phase focuses on understanding what the system must do. It involves gathering requirements from users, studying the problem domain, and identifying constraints or assumptions. The outcome is a set of precise, validated requirements that guide design and implementation. During design, engineers create the structure of the system. They define the architecture, break the system into components, specify interfaces, and select data structures and algorithms. Design models help visualize how the system fits together, setting the stage for efficient implementation. Implementation involves translating design plans into actual code. Developers write modules, follow coding standards, and integrate components into a functioning system. This stage transforms abstract designs into a real working product. Testing ensures that the system works as intended and meets its requirements. It includes unit tests for individual modules, integration tests for combined components, and system tests for the entire software product. The goal is to detect defects early and deliver a dependable, high-quality system. Black box testing focuses on inputs and outputs without looking inside the code, ensuring the software meets its external requirements. Glass box or white box testing examines internal logic, ensuring that paths, conditions, and structures behave correctly. Combining both approaches provides strong overall quality assurance. Documentation records the information needed to understand, maintain, and evolve a system. It includes requirements documents, design diagrams, code comments, and user manuals. Good documentation ensures consistent communication across teams and helps the software remain usable and maintainable over time. The waterfall model follows a rigid sequence of phases, each completed before the next begins. It offers clarity and predictable milestones, making it suitable for projects with stable, well-understood requirements. However, it lacks flexibility if changes arise later in the development. The incremental model develops software in multiple small releases each adding functionality to the previous version. This allows users to see early results and provide feedback. It offers greater adaptability while still maintaining structure. Prototyping involves building simplified versions of the system to explore ideas and gather user feedback. It helps clarify requirements, reduce misunderstandings, and identify design issues early on. Prototypes guide teams towards better solutions before full development. Open source development relies on collaborative contributions from a global community. Code is publicly available, encouraging transparency, rapid iteration, and continuous peer review. This model has produced many robust, widely used systems across industry and academia. Extreme programming is an agile method focused on rapid iterative development with strong customer collaboration. It uses practices like pair programming, continuous integration, and frequent testing to improve quality and adaptability. XP values responsiveness and continuous improvement. Modularity breaks a system into smaller, self-contained components with clear responsibilities. This makes code easier to understand, maintain, and extend. Modular systems reduce complexity and enable teams to work more efficiently through reusability and isolation of changes. Coupling describes how tightly connected different modules are. Low coupling means modules interact through simple, well-defined interfaces and do not depend heavily on each other's internal details. This improves flexibility, reduces the risk of changes causing widespread issues, and supports reuse. Cohesion refers to how strongly the responsibilities of a module belong together. High cohesion means a module has a single, well-defined purpose, making it easier to maintain, test, and understand. Systems with high cohesion tend to be more reliable and efficient.